let's kick off this webinar. So it's a pleasure to start this webinar, introduce it. My name is Alberto Trocli. I'm the coordinator of the SECLI-FIRM, which is an H2020 EU project. And we are also here joined by a representative from the CLARA project, which is great. So the discussion today is about climate services for the hydropower sector, and specifically trying to see how the climate information is used in practice to turn climate science into solution for the hydropower production. Before we do that, with the presentations we have today, we got three great presentations showing three separate case studies. We want to give you a bit of an overview briefly about the SECLI-FIRM project. So I'm going to give you this overview, and in SECLI-FIRM we are dealing with 9 case studies, nominally 9 case studies, which are covering mostly the energy sector and mostly over Europe, but we also have water sector and South America, particularly Colombia. So quite a range of case studies, and you can see the details here. I won't go into detail, but what we're trying to do is to use the best science from seasonal forecast to provide solutions for these case studies. And while we do that, we also want to assess the value of the seasonal forecast. So one of the main aims of the project is to assess the value, and we do that using different methodologies from the economic literature, and it's really based on a simple approach where we take the control group, which is based on climatological information, which is normally the standard information used by this type of decisions, and then we add on top of that the seasonal forecast and see how the decision is changed, depending on also how we evaluate that in terms of methodology we use. I'm just giving you a very high level presentation here. I won't go into the details of the methodologies and so on. I'll give you the references at the in a few minutes so you can go and learn more if you're interested. But just to dig a bit deeper on the methodology, we have developed for each case study a decision tree. This has been crucial and very useful to understanding the type of decision making that is done in each case study, and that actually helps us a lot to assess the value. So this has been a very useful exercise, not particularly easy, but I think we've achieved quite an important milestone with this production of decision trees for each case study. And then, without again going through the various steps, we come to some kind of end. The project is now running in its last year. Out of about 3.5, so we're starting to get results, and one of them is represented here, where we have the decision tree that is converted into information coming from the forecast, and we are able to map what is in the decision tree with the kind of traffic light type of information, which is telling us whether a period is good or bad depending on the climate, the seasonal climate information that we obtain and elaborate through various methodologies. So this is one way to represent the climate service. So we explored for each case study, or there are groupings, but we adopted this approach of exploring different ways to present and develop a case, like climate service, because it gives a very broad idea and broad spectrum and a good idea of what can be achieved through climate services. And indeed, it clarifies also, helps clarify what climate services are. There's no unique definition and no unique way of delivering it. Another way to deliver it, though, is more graphical, and we're also developing a user interface, a web interface. So this is yet another way to deliver climate services. So as I said, there are various ways, and if you like to learn more, we have for each case study a flyer, a 4-page flyer or document which explains what each case study is about, and all the flyers are set up in the same way, following the same logic. So once you read one, it'd be easy to follow all the others, or it should be. And if you have questions or if you're interested, please get in touch and we can tell you more. And the website is under here. You will receive all the copies of the presentations that will be shown, uploaded on our website. So you can find out from there also about all the details that we are presenting today. So going back to the presentations, that was my short overview of SECLI-FIRM and a bit of introduction to the webinar. Well, we focus quite a bit on hydropower in SECLI-FIRM, and indeed the first 2 presentations are from SECLI-FIRM case studies, and the third one is from our kind of sister project, CLARA, also developing a similar climate service for hydropower. So it's a pleasure now to introduce Mattia Caligari from EURAC, who is going to talk about the runoff of seasonal forecast in alpine catchments, a SECLI-FIRM case study. So I'll switch over to Mattia, and the floor is yours. Thank you, Mattia.
Thank you, Alberto, for the introduction. Please let me know if you can see my screen now.
Yeah, perfect.
Okay, thank you. So, yeah, I will try to show in this presentation what we developed in the SECLI-FIRM project about a method for runoff seasonal forecast in alpine catchments, and I will in particular show an application of this methodology on a case study of the project that is related to the hydropower system in South Tyrol in northern Italy, where that is managed by Alperia, which is the local energy provider. Okay. So in general, we can say that the seasonal forecast of the runoff from 1 to several months ahead is a quite relevant application for hydropower plant management, since the estimation of the seasonal runoff can be used to optimize the current and the future energy production. It can also be used to predict the energy that will be produced by a specific hydropower plant system. And also the seasonal forecast of the runoff could also be used to improve the management of the artificial basins to prevent the risk of floods and to reduce the impact of drought. So this is an overview of the case study that I will focus on in this presentation. This is an alpine catchment in Ulten Valley that is located in South Tyrol in northern Italy. It's a typical alpine catchment where Alperia has one of the most important hydropower plant in the region. At Alperia, for managing this hydropower system, they are using a model that is called Hydro Tool, which takes a number of inputs, including the forecast of the seasonal runoff in the basin, to get an estimation of what is the optimal reservoir level of the water that they should keep in order to optimize the energy production. And the model gives also an estimation of the energy production that can be produced. So our objective here was to develop a methodology that is able to provide reliable input regarding the seasonal forecast of the runoff for this model, so that Alperia can use this forecast to improve the output of this model, and therefore to improve the management of their hydropower system. The model that we developed is using seasonal forecast data, and while implementing the method, we also tried to minimize the requirement of in situ data that are needed to run the model. This is because we wanted to develop a method that could be easily applied also to other areas where maybe the collection of the data of in situ data may be difficult. So in general, when we speak about the seasonal forecast of the runoff, we have to estimate firstly the catchment state variables, which tell us what is the amount of water that is stored in the catchment just before the forecasting period starts. And this can be expressed, for example, in terms of soil moisture in the catchment and snow water equivalent. Then we also have to estimate all the positive and negative contribution that can contribute in the runoff during the forecasting period. And these are, for example, the rainfall, the snow melt, and the evapotranspiration. So instead of using a hydrological model, we decided to use a machine learning approach. In this way, we didn't have to estimate every single component that I was mentioning in the previous slide, but using machine learning, what we can do is to try to select some proxy variables that are easy to retrieve and that are related to all the components that I was listing before, and try to find then a function that can map these proxy variables into the estimation of the runoff. So try to keep the model as simple as possible in terms of input that are required to run the model. We decided to select time series of temperature and precipitation as input, both for describing the catchment state, because of course time series of previous temperature and precipitation are of course related to soil moisture and the snow water equivalent that we have in the catchment. And we also use the temperature and precipitation for as a proxy variable to describe the main contribution that we have during the forecasting period. Also in this case, in fact, the temperature and precipitation are surely related to rainfall, snow melt, and evapotranspiration. So since we decided to minimize the requirement of in situ data, we decided to use ERA5 reanalysis of temperature and precipitation for describing the catchment state before the forecasting period, and the seasonal forecast of temperature and precipitation downscaled on ERA5 to describe the contribution, the future contribution during the forecasting period. This is the general workflow of the method that can be divided in two phases. The first one is the training phase, in which we only used time series of temperature and precipitation derived by ERA5 data, and the target in situ runoff on which we have to train our model. So during the training, we also select the optimal length of the time series of temperature and precipitation that can better describe the catchment state before the forecasting period. And once we train the model, we are ready then for going operational. So the prediction phase can start. In the prediction phase, depending on the lead time of the prediction, we are combining time series of temperature and precipitation from ERA 5 and temperature and precipitation estimated through seasonal forecast downscaled on ERA 5. Once we combine these two, we can then fit our machine learning model and doing the actual seasonal forecast of the runoff. So for testing the performances, we applied our method on our case study in South Tyrol, in the Ulten Valley. And for testing the method, we implemented a leave one out cross-validation strategy where iteratively we used all the years except one for training our model, and we tested the results on the year that was left out from the training. Then we also select a benchmark method for comparing the performances of our proposed method, and this benchmark method was identified as the runoff climatology, since this is actually the method that Alperia is using for producing the input to their hydro tool model. Additionally, for computing the performances, we also tested what is the effect of different length of available runoff time series that are available for training our model. This is because the runoff time series is the only in situ measurement that is needed for running the model, and we know, of course, that depending on the catchment, is not always easy to have a long time series of the runoff. Therefore, we wanted to test how the method performs with different lengths of runoff time series. So we firstly trained our model, and we was looking for the optimal length of the time series of temperature and precipitation that can better describe the catchment state before the forecasting period start. For this particular catchment, this was identified as a time series length of 7 months of temperature and precipitation, and this is quite realistic if we think that we are facing with an alpine catchment where there's no contribution, so there's no accumulated during winter, is one of the most important contribution to the runoff, and that's why 7 months that can take into account all the phenomena for snow accumulation is needed for temperature and precipitation. Then once we have our trained model, we run it with our leave one out cross validation strategy, and we computed the root mean square error. Here in red is what we call the perfect forecast of our model, in which we are not using any seasonal forecast data for temperature and precipitation, but we substitute all the temperature and precipitation of the seasonal forecast with the actual ERA 5 reanalysis values. In this way, we can have a sort of upper bound of the performances of our method, because we remove all the errors coming from seasonal forecast. In black, instead, we have the error that is done when we are using our benchmark, that is the runoff climatology. And for computing the runoff climatology, we are actually using the same number of years that are using for training our model, so that we have a more consistent comparison with the performances of our model. In fact, here in the x-axis, you can see the number of years of the runoff time series that is used for training the model. With all the other color, instead, you can see the root mean square error with the different lead times from 1 to 6 months for the prediction of our runoff. The good thing of the result is that for every lead time, we have a root mean square error that is lower with respect to our benchmark. But of course, as expected, the higher is the lead time, and also the higher is the root mean square error. So concluding, we have seen this method that we developed in SECLI-FIRM that is based on a seasonal forecast downscaled on ERA 5 for seasonal forecast of the runoff. For the specific case study that we analyzed, the method outperforms the runoff climatology that was our benchmark for all the lead times that we considered from 1 to 6 months. And therefore, that's why we think that this method could provide a more reliable input to the model that Alperia is using for managing the hydropower system, and therefore they can use it to optimize the energy production and increase the overall profit. So that's all from my side.
Okay, thank you very much, Mattia. Yeah, so we will have times for questions at the end. So we go presentation after presentation. So that was great. Thank you, Mattia. And now we have a presentation by Christian Nielsen from UL. And also from SECLI-FIRM, and seasonal forecaster of hydro resources in Colombia during strong El Nino events is the title. So for everybody, please, so while Christian gets ready with the presentation, we encourage everybody to type your questions. So you can start to type them now, we collect them, and then we will address them at the end. So thank you. Over to you, Christian. Thanks.
Okay, thank you very much. Let me share. Okay, let me know if you cannot see my screen, but you should be able to now. Okay, so I would like to present to you what is known as case study 5 in the SECLI-FIRM, and I would like to present our methods and also some of the first results. As Alberto just introduced, my name is Christian Nielsen, and I work in the Barcelona office of UL. So let me see that. So if we start out with a summary of case study 5 and what it actually involves, this is a case study that's slightly different as it is located in Colombia, unlike a lot of the other case studies that have their focus on Europe. So of course we have some different driving factors here than we have in Europe, and of course that has also led to slightly different methods. So our end user in this case have been Celsia, and we have been working with them in order to try to improve their existing deterministic forecast of river flow. And the reason that was chosen to stay with something relatively, you might say, simple as a deterministic forecast is that Celsia was using this currently, and therefore it would be an easy implementation and an easy test to see if we can actually improve this compared to them having to change their entire internal decision system and also their econometric models. So there are different ways that we've tried to come up with these forecasts for river flow. We've tried a direct forecast. That means that we have tried to estimate the precipitation over each of the catchment areas for the dams, and that way come up with a correlation which obviously is there with river flow and being able to forecast the river flow. Secondly, we've also tried a teleconnection forecast, as I've called it here, which is utilizing global teleconnection patterns, because we all know that in this area of the world there is a strong connection between sea surface temperature anomalies, especially in the Pacific, but also other places, as I will show you in a second. And therefore we also tested out this, and currently we're also testing this machine learning method called random forest in order to see if we could improve further by adding observations from the past into the prediction. So what I'm going to tell you today is mainly focused on the teleconnection forecast, and that is because this is what have shown quite good results, especially for the periods and times that are of interest of Celsia, which is of course when they have their droughts that are strongly connected to these El Nino events. So first of all, how do we actually get from sea surface temperatures to river flow? Here's just a short overview. What we've done is we've tried to estimate a teleconnection patterns between the observed sea surface temperature anomalies and the observed river flow for these stations of interest to CELSIA. And we've done this on a monthly basis where we've tried to make very specific patterns by finding the patterns and then removing the areas that are insignificant and also some areas of inconsistence. When I say inconsistent here, it's because there were some areas with sea ice and so on, but I'll get into that in a second. Forecasting, and then finally we are going to forecast the river flow from knowing these specific teleconnection patterns that we have found for each river. So allow me to go a little bit more into detail for all of you. First of all, what we did was, of course, to look at these well-defined areas. A lot of you will probably know them, and I've plotted, I have not, but I've attached a plot here to the left, where you can see one of the areas that are normally referred to in literature and normally also used. But what we saw, I mean, we did this and we got good results. I'll show you some numbers at the end. But what we saw in our study at the beginning was that maybe there are also other places in the global seas that has good teleconnection with this specific river. So as you see on the map here to the right, it seems that there are areas that has good correlation, either negative or positive, with river flow for this specific river that in this case is called SAL. It's just a station for this specific river that has interest to CELSIA because it's located close to one of their dams. So what have we done? Yeah, we've done that. We've looked at the period from 1993 to 2016. And there we found for each year and each month, we found the correlation between that specific month by looking at all the other years. So we have made a cross-validation, leaving one out here, where we found the specific correlation for that specific month. So in April 2009, as you have an example here, you see this is the correlation from all the other Aprils from all the other years. And we've done that for each year in order to then validate our forecast for that by running it for that specific year. And then, as mentioned, remove all the points that we consider non-significant, sorry. And at the end, there's also removed, it maybe not that visible on this map, but if you can see my pointer, we have also removed some areas that, due to some model having sea ice and other models not having sea ice, gave some quite wrong results. So there are some areas close to the Arctics that has been removed, and both Antarctica and Arctica, that simply has been removed due to inconsistency between the models and therefore some results that were untrustworthy. Here's another example. We've done the same as I mentioned for all the months. I can't remember specifically this year, but this is a December month for one of the years. And as you can see in this case, for example, you do have strong teleconnections with the area in the Pacific as expected due to the El Niño. But in the other months, as I showed, there are also other areas that seems to might be able to improve the forecast by utilizing these areas as well. So from having found these areas that has strong correlation with our river flow anomalies in this specific river that we're looking at in this example, we can then say, okay, what if we then use to forecast the sea surface temperature globally for that month instead of using observations? That way we actually end up having a forecast of what is going to be the difference in river flow that month. So if you see here on the map, this is a forecast from the month before, and you can see that there are big areas here that are colored red, which means they are drier than normal, or they would imply that our river in Colombia, located here, will be drier than normally. But there are also areas that are more blue that would imply the opposite, that we would have more wet than normal. But overall, if you average over the entire oceans of the world, you actually end up with a forecast in this case that fits very well. We can see the same here. This is a year later, so in 1999, we are now out of the El Niño event, actually going into El Niño as far as I remember. And you can see this is quite a different picture. Most areas now predict that there would be higher river flow than normally, and which was also the case, even though here the forecast didn't really capture the entire size of this anomaly.
Christian, sorry to interrupt.
No problem.
I don't have any problem seeing your slides and your camera, but some people are saying that they cannot see your slides. They can only see you. Perhaps
I will turn off my camera. I apologize.
No, it's okay. I mean, it was working for me, but some people. So yeah, sorry for the interruption. So hopefully that fixed the problem for everybody now. Thanks.
Okay, I hope that fixes the problem. Yes. But as I mentioned, yes, this is one of the examples of a forecast where we have found the teleconnection patterns for this specific river in Colombia for this specific month by using all the other years. And there we have then added, by knowing this correlation, we've then added the forecasted sea surface temperatures in order to forecast an anomaly for each of the points in the ocean that were significantly important. I hope that summed it up for those of you who couldn't follow the first slides. I apologize. So if we then look at a slightly longer time series, here again we have the same stations that are of interest to our end user. What we have plotted here is just the years against the difference in percentage. So when we have 1 here, it means that there's 100% more river flow than normally. As you can see in Colombia, there are quite big anomalies to be observed. And then if we plot the forecast using, here I've used quite a selection of different models, but as you can also see, they don't vary too much. And what's important to see here is that the El Nino event that I have marked out, with this method, we are able to predict the anomalies quite well. This is with a lead time of 1 month before. So for example, a forecast for January for the February month. But we are still able to forecast both the onset and the offset of these specific events to quite a good degree, which is of course which is important for our end user Celsia in this case. And as I mentioned, the models individually don't provide too much difference. This is also due to the fact that sea surface temperatures is quite well predicted by most models, and also with a lead time of 1 month, there are not too many differences initially in what the models predict. So as I mentioned at the beginning, we've also tried different methods. So there are also different results, of course. And what you see here, the top bar, is the method that I just explained to you. And as you can see, our result is actually with this method at the moment the best. Here it seems like we've only tried 4 different things, the teleconnections using the defined areas, which also give good results, but there are still improvements to be found with the method I just explained. The random forest method have also showed some skill, and we are still working on improving that, maybe adding further forecast data in order to get better as one of the things we use to predict with. And I think we can also still predict, we can still expect further improvements from this method. And finally, we had the direct forecast over the catchment area that shows the worst skill here. Of course, it's not a direct forecast per se. We have gone in and we have done some quantile mapping in order to downscale the precipitation data from the forecast models, and also bias corrected, and that way come up with better results than using the raw data, obviously. But unfortunately, this area that we're looking at, the topography, is very difficult because it's simply not included in this forecast model that works on a 1 degree grid. So we have values that are not represented in the models, and therefore the stations that we actually have in the area, the correlation between the ERA 5 data, for example, and the stations are not it's not very good. So that's why we ended up with the specific method that we're working at the beginning. And I think we can also say that this method is better than what Celsia has been working with so far. So one of our next steps now will of course be to try to come up with an estimate of the added value that Celsia would have from using this specific methods. We are working on this, and I hope that it's results that we will have in the near future. But obviously it's difficult for all of these companies to share everything publicly, so that's also why I don't show you any more numbers here. But we are working closely with them, and we will hopefully have some exact numbers of what the improved skill would be. And then finally, we are also working on a second scenario, because as I showed you earlier, the model that we have developed here captures the El Nino events very well. Allow me to go back 1 second here, sorry. But in the more normal conditions, we don't seem to capture all the variability, which of course are not the most important moments for our end user, but still we would like to improve this, and hopefully by combining the different methods, we can come up with a better forecast at the end. I think that was all for me. I apologize if some people were not able to follow the entire presentation, but I will leave the word to you again, Alberto.
Yeah, thank you very much, Christian. I think, yeah, it seems that the problem was fixed in the end, and it was to do with individuals' terminal computers and so on. So not to worry, but also, as was shared on the chat, we will share all presentations and even the recording of this session. So you will be able, if you wish, to go back and look at all the slides and the beautiful colors from Christian. So now, I remind you about the questions. Please keep typing them, and we'll address them after the next talk, which is now by Paolo Mazzoli from GECOsistema, and presenting a case study from the CLARA project, another EU H2020, which I believe has just completed or is about to be completed. And it's about Smart Climate Hydropower Tool and an artificial intelligence or augmented intelligence-based service for hydropower production seasonal forecasts. Over to you, Paolo. Just a minute, I'll give you the floor. And thank you very much for contributing to this webinar.
Thank you, Alberto. Thank you all. I'm sharing the screen now. Good morning, everybody. Paolo Mazzoli from GECOsistema. And I'm going to show you this Smart Climate Hydropower Tool that we developed inside CLARA that just ended. It's an Horizon 2020 project that ended last month. In this project, we focused on developing services based on seasonal forecasts, which are increasing and growing in availability and popularity. Concerning Smart Climate Hydropower Tool, we developed this service for hydropower in close connection and collaboration with Enel Power, which is one of the major players in energy and renewable energy with assets worldwide in the hydropower sector in this case. We developed this starting from the needs of our user in Enel Power. Particularly, they needed to understand and evaluate how much Copernicus seasonal forecast and can help in contributing, reducing uncertainty on hydropower production that is related to the natural inflow variability. So we could solve this issue in a standard way, I would say, using a hydrological rainfall runoff model in order to try and guess the available incoming discharge to one hydropower reservoir. But we need, in principle, if we follow this path, we need time, we need data, topography, land use. So we probably need the involvement of an expert, an hydrologist, for example, and we need to set up multiple models for multiple sites. So the request from our user, from Enel, was quite different: to get something, to prove something that can be then easily replicated in worldwide. Virtually in every hydropower plant and reservoir, they can have in South America, in Europe, and everywhere around the world. So that's why we have gone, we followed another path. I mean, we have gone through a data-driven approach using machine learning, again, quite popular in this webinar, I think, in order to combine Copernicus seasonal forecast with local data from Enel, discharge, recorded discharge particularly, and provide the forecast without the need of a mechanistic model. In principle, this can lead to, I would say, a more democratic use of seasonal forecast. Now, it doesn't need a true expert to make a forecast. In principle, it requires less time and can be replicated worldwide in every site of the company, because the data, Copernicus seasonal forecast and own site-specific discharge data should be available in every single plant of the group, and can be then translated easily into a service, a web app, a web service that can be provided to the user. Where can be the value of providing a forecast for hydropower? We tested this approach in two reservoirs in Colombia, Betania and Alguavio. As you can see from the number, a few thousand gigawatt hour per year of production, these are relatively big to be small hydropower plant, I would say, in which Enel faces some problems related to the forecast. That one is, under a technical point of view, the management of the reservoir that can be improved, that can benefit from knowing in advance discharge in the incoming months, and eventually even a financial one. So there's a problem in selling and buying energy, an issue, that lies in the deviation between the scheduled and annual production that you put at budget and what you can actually achieve. Having a discrepancy between these two values needs corrective actions that could be basically selling and purchasing energy. If you buy energy, you face usually increasing unit cost during the year, and if you sell the redundancy, you get usually decreasing benefits the year round. So the objective is to know as early as possible what's going on in order to take the most advantageous decision. How we did solve this issue? We have relied heavily on the Copernicus seasonal forecast, particularly the seasonal forecast of precipitation and temperature that are now available through the Copernicus data store and can be accessed by the toolbox or by the API, can be downloaded. As you see from this picture, compared to the catchment size that is upstream of each of the plants, this is a relatively coarse information at 100 kilometer resolution, the pixel size of this information. So we explored all the pixels, roughly speaking, around the catchment, and we extracted the time series, the signal of precipitation and temperature forecasted 1, 2, up to 6 months in advance around the basin. And then decide to go for the ensemble of the 9 numbers available. Again, how we did this, without bothering you too much with the, I would say, with the technical aspect, we did some feature selection. We tested every and each of the signals in order to see, for example, through the correlation matrix, if there is some signals that basically brings the same information than another, some pixel temperature signal, for example, with the same highly correlated to one of its neighbor. And also we run some machine learning approach like the tree-based relative importance variable in order to guess which is the most informative feature among the available one. Precipitation temperature, at which lead time, and in which geographical area, in which pixel we can get the most informative signal. And then we feeded this information together with the Enel Green Power own monthly discharge data, testing many machine learning algorithms. We have done either testing single algorithms like sample vector regression, the same that Mattia was showing, or deep learning. And we have also tested one of the many available auto machine learning platforms that can make you run multiple tests with multiple parameter configuration, multiple algorithms at once. Comparing then the results versus a baseline benchmark that you can get, for example, by the climatic average, or in this case, also having an alternative source of forecast, a regressor that Enel Green Power set up independently in-house. We have chosen this way. We have decided to, let's say, tune the forecast algorithm in the first roughly a little less than 20 years of data, and then test in the last 4 or 5 years of data independently, blindly, to see the performances. We have tested, of course, our forecast based on machine learning and the alternative, the baselines. But again, not stressing too much on the numbers, we can get usually better results, either in Betania or Guavio, 6-month or 3-month forecast of cumulated discharge shows better performance metrics, in this case, root mean square error, compared to the benchmarks, either climatic average or multiple regression. But this is not probably the part I want to stress you more on. It's more on the, let's say, the framework, the way we set up a service on this idea that you can see here. We have set up a workflow, operational workflow that can run every month, producing an operational forecast, starting from downloading the Copernicus data store forecast of precipitation and temperature, coupling it with local data from Enel, in this case, discharge, and then be pre-processed through some code that we developed in-house based on Python in order to store information in a database and feed the trained machine learning algorithms in order to provide energy production forecast through a web service. So in the end, on Enel's side, what you see is a web page in which you can get access to the history and the forecast in terms of time series of all the variables that we have used to feed the forecast and all the available forecast source, either the baseline and our provided machine learning based forecast. Together with this capability, you can zoom in a period of interest in order to check out who worked better than who, and being provided, for example, the error distribution and the standard lumped performance metric like root mean square error or Nash Sutcliffe coefficient. Again, jumping back to the first, I would say, slide, where is the value of doing all this or setting up a forecast service based on seasonal forecast? We have developed together with them this little what if exercise. I mean, we have tested what applying the usual rules in the Betania reservoir, use of management rule, basing this management rule on the climatic average forecast, for example, and basing the same management rule on the knowledge in advance of the forecast that we provide. And we have make a simulation of how the production, energy production can change. As you can see here, for example, we got sort of an improvement in production of a few percentage point that translated to a 2,000 gigawatt per year plant makes roughly $500,000 per year, more or less. So, I mean, that in such a big plant, that alone fully justifies to, I would say, go and set up a better forecast through such a lightweight, lean approach, I would call it. That is relatively low time consuming and can be, let's say, rely only on available data, local and global available data. And again, if you compare this gain to the maximum gain that you could have with the perfect forecast, that is a few percentage points, again, you see that the seasonal forecast can squeeze out, roughly speaking, a little less than half of the extra value compared to a perfect forecast. So again, it makes sense to make a forecast based on such a technique to set up a service based on such approach, and there's definitely an added value in the Copernicus seasonal forecast according to this experience that we have that is ended, as I said, in the CLARA, together with the CLARA project last month, basically. So it's all from my side. Thank you all for your attention.
Okay, thank you very much, Paolo. That was a very good demonstration once again of the power of the statistical model. So I guess we've had a festival of statistical models for hydropower generation, and this seems to be a good way to go. We got now time for questions. We can go for about 10-15 minutes depending on the questions, so we please keep typing them. We have a few already, and I'm actually going to show them on the screen so we can all see them. And the first question is for Mattia, and the question is, you compared with benchmark climatology runoff. How would your methodology compare with runoff predicted directly by multi-model ensemble seasonal climate prediction systems collected in SECLI-FIRM? Thanks, Mattia.
Yeah, this is something that that we definitely have to try. What we need to do this is since the method for seasonal forecast of the runoff use temperature and precipitation data coming from ERA 5, and all the training of the model is based on ERA 5 time series of temperature precipitation. what we need to do if we want to test the capability of the MME, seasonal climate prediction, is what we miss is to downscale these to ERA 5. But for sure, then once the downscale is done, then this is something that we definitely could test.
Okay, thank you.
Should I go on with the second?
Just so yeah, there is well, just let me read it out for everybody. So, hi, I am Ignacio, and thanks for your presentation. Did you show results for just one alpine basin? Did you test this methodology in other alpine basins? Is there any relation between scale of seasonal forecast and mean elevation of the catchment? Thank you.
Yeah, also this is something very interesting to be tested. At the moment, we actually tested the method only on one alpine catchment, that was this catchment in Ulten Valley in South Tyrol in northern Italy. But for sure, it will be very interesting to test on other alpine catchment to see if there is a relation, as you suggested in the question, with some characteristic that some catchment have, like mean altitude or the presence also of glacier, the amount of contribution that the snow gives to the runoff for a particular catchment or another. So this is a quite relevant analysis that we definitely should go on. But yeah, for the moment, we just tested the method on the catchment that I presented here.
Thank you, Mattia. And then there is a question for Christian now.
But what I showed in my graph is, of course, the ensemble mean from each of the actual variability in these models, and it becomes overconfident. What we could do in this sense is, of course, to try to look more at the individual ensemble members and perhaps run the method for all of them, and then we could find a spread after that. But the reason that it looks like it does at the moment is that SECLI at the moment, they handle these uncertainties internally in their econometric models, which to some degree builds, as far as my understanding is, on climatologic values, which of course could be improved if we were able to, for example, for specific cases, hand them specific uncertainties, depending on what the model, what the spread were for the individual ensemble members, for example. So I hope that explains it. It's mainly because of the demand of our end user that there are no uncertainties added at the moment. Actually, we just use an average of all the averages of the individual models to come to a final forecast. I hope that answered.
Yeah, thank you, Christian. And then we have a question for Paolo. Could you elaborate on the machine learning methods used, perhaps LSTMS, linear or something? You know what it is?
Yeah, that sounds familiar, thanks. This question is what runs under the hood, I mean, of the service. We have tested many algorithms, including long short-term memories, which is particularly, to my knowledge, suited for time series forecast. We also tested subprogramming regression and on some other regressors. But again, what was, I would say, also interesting, going down to this choice of algorithms, was also the capability to test through open machine learning platforms many algorithms together. So we have, in the later stage of the project, we have followed another path, that moving from fine-tuning a single algorithm like long short-term memories to testing many algorithms through machine learning, you're getting slightly better performance than heavily focusing on only one algorithm, such as the one that was mentioned. So we have tested many is the answer, and we also tested auto machine learning platforms to test even many more at once. I hope this answers.
Okay, yeah, thank you. And there is another question which I don't have time to type. So general question for all presenters. It seems to me that the forecast of extreme low and high runoff has the most value rather than the overall fit of the true runoff curve. I would imagine a value-added product when focusing more attention on trying to catch the extreme low and extreme high and rare events. Maybe a good opportunity for all speakers to give their view on this, and then just as brief as you can, and then we can wrap up and close. Thank you. I hope the question was clear. Otherwise, let me know. So maybe, I don't know, do you want to start, Mattia?
Yes. So yeah, this is a very good question. I also showed the results only on average, but for sure it would be interested to focus more on the extremes. I think there are several ways to address these. Okay, the easiest one would be just to keep the model as we implemented. So train the model on all the cases that we have, and then just to see how the model performs when these extreme events occur. But I think in general, another alternative solution could be to develop specific model in which we focused only on extreme event, so that the model is trained only on this, and try to develop a separate method that can identify when this extreme event occur, and once the extreme event is identified, then pass it to the model for focused on extreme event only. I think in this way, probably the extreme event could be better forecasted, but this is definitely something that has to be tried. So yeah, so thank you for the question. I think it's a relevant point. I like the answer to also the other.
Okay, thank you, Mattia. Maybe Christian, do you want to answer
quick
this?
comment. I mean, I think from my presentation, it's also clear that we've had focus on these extreme El Niño events, not only because they're well predicted, but also because they have a big impact on our end user. That being said, we still also hope to combine this method that I showed that can predict some of the extreme events, at least the extreme drought events, with other methods in order to capture more of the variability under more normal conditions. But yeah, I think from our side, focus has always been on having a method that at least is good at predicting the most important events to start with, and then hopefully we can come up with some combination now, either using machine learning or more simple matters where we can use slightly different methods depending on what's being forecasted for the different systems in order to try to capture the whole picture better. Thank you.
Okay, thank you, Christian. And finally, Paolo, would you like to give your view on this point?
Yes, even if our service works totally on the other side, we are working with seasonal average 1 to 3 months in advance forecast, so we are totally on the opposite side. But it's still a fascinating question because it gives us the opportunity maybe to reflect on the capability of data-driven approaches that are quite flexible. And for example, just feeding a similar workflow with extreme events time series could lead to the devoted and dedicated forecast for the extremely low or extremely high. So again, I think it's a field in which the same workflow, the same machine learning basic approach could be challenged quickly and interestingly, testing what's coming out of it.
Okay, thank you, Paolo. And we are now running over time. So let me thank all the speakers and the organizer also of the webinar, the SECLI-FIRM team, and all the attendees for your participation. And I just want to refer to the website of SECLI-FIRM, Twitter account, LinkedIn, and so on. So we have more webinars to come and other activities. So please keep an eye on our social media channels, the website, and so on, or get in touch if you're interested to learn more. Be happy to hear from you. And until next time, thank you very much again. Bye-bye now.